So, welcome to the first key lecture that we're going to do in week number 5. As you all know, in week 5 we're mostly doing readings, and the readings are a wonderful skill to pick up since so much of your learning after this course will take place in this way. But it's nice to have a variation from the lectures to have the readings, and it's nice to have a variation from the readings to perhaps have a lecture and get back to my raspy voice again. What we'd like to do in this one is just emphasize some of the material that's done so well, I think, with respect to the thermohaline system that's discussed and the ocean current system that's discussed in chapter 9 in the book. Remind you of the key structure that we're dealing with in the ocean. We've got this basic structure of a two-layered ocean that exists over much of the temperate and tropical waters. The heating from above produces a highly stable situation with a warmer temperature, and that's accentuated by the fact there's a shift in density. So we go to a higher density at lower levels, and we also go to higher salinity at lower levels. And you now know the explanation of this, that the reason why this structure, well, particularly the structure in the density and salinity, takes place because of the nature of the instability in the ocean that occurs at the poles. That instability associated with the cooling that takes place, particularly winter, but also the formation of ice, which separates the salt from the water. And we end up with this highly stable structure. That stable structure suppresses mixing as a tremendous barrier against mixing across the ocean. And what makes this particularly challenging for Earth as a whole is the fact that organisms live very effectively in this high illumination portion of the ocean where there's still a lot of photons. They can grow in here because they've got energy and light to be able to allow them to grow. But the problem is that they don't have a good supply of nutrients. The reason for that is that when they grow, when they fix carbon dioxide from the ocean and they turn that into their various forms of body mass, many of those things that they form are denser than water. And as a result, when those organisms die or produce pellets as a result of their digestion system, some of that material drops down due to gravity into the lower layers. And that produces a net migration of nutrients from the surface waters into the deep waters. And because of this suppression due to mixing, this high nutrient material, which is also reflected in this structure, can't get back to the surface. And so where we've got lots of nutrients, we don't have much light. Where we have lots of light, we don't have many nutrients. And this is a great challenge. What chapter 9 gives us the explanation for is the fact that much of the Earth has this problem of basically the ability of oceans to produce a lot of life, their fertility, but there's a few places where this is resolved, and that's what chapter 9 helps us to understand. To understand that, we have to understand a little bit of a complication first, but it's leading to a partial solution of this two-layer ocean. So let's quickly recap what we've learned so far. Differential heating and cooling causes temperature and density differences, as we've discussed. These density differences act through gravity to produce pressure differences, which tend to induce flow. The flow itself is modified by friction, and since this ongoing process of day and night, of areas with land and areas with water, of seasons, is continually take place, there's a tremendous complexity taking place here. But there's another fact that we haven't talked about really since the beginning of this course, and that the Earth is rotating. It's not rotating that quickly. In fact, by definition, really, there's one rotation per day. That is the basic definition of what we mean by a day. But large-scale motions are influenced by this fact. One rotation per day, if that were on a turntable, you'd hardly notice. We're not that aware of that rotation moment to moment. But over large-scale distances or over large amounts of time, those things do accumulate, and it gives rise to an effect associated with that motion, which is associated with Coriolis, who was the first person who really identified that there would be a deflection in all these fluid velocities associated with that. There's two key facts that we want to emphasize here is that the deflection of fluid velocity increases with latitude as we move away from the equator. It's actually zero at the equator and maximum at the poles, and increases linearly with velocity. The second fact is that this deflection is different in the different hemispheres because as we look down on the Earth, the rotations are opposite, looking down on the North Pole compared to looking down on the South Pole. And deflection that's produced is the velocities are deflected to the right in the Northern Hemisphere and to the left in the Southern Hemisphere. And this gives rise, as the book discussed so well, to this fascinating thing called Ekman transport. This was first identified by Ekman, and it really has to do with this interaction between wind and surfaces, between friction and this effect of the Earth's rotation called this Coriolis effect. And what we basically have here is that the wind produces a drag on the surface of the ocean, which tends to induce the water to move, but that force is acting along with this force to the right caused by the Earth's rotation, and produces a net surface effect, which is deflected at about 45 degrees typically to what the wind direction is. But the surface waters start to induce deeper waters to move, and they also are deflected to the right. They're also diminished because they're a derived flow. They are less than the surface flow. And these somewhat subsurface layers produce even more deep layers to produce motion as well. Each of them, at each level as we move down, is deflected further and further to the right, and each one is diminishing. And this produces this characteristic called the Ekman spiral, with all the deflections to the right, as they're shown here in the Northern Hemisphere, and you simply have to reverse the curl in the Southern Hemisphere, where all the deflections are to the left. Deeper layers will move less than the shallow ones because of the influence of the derived motion and the basic essential nature of friction. And it's quite possible for them to complete a complete spiral, or perhaps even more under special circumstances. This is a kind of complexity, but it's also a delightful surprise, something that we wouldn't expect, that we get a net motion of this current, that's at quite an angle to the wind. In fact, to a very large approximation. If the wind is in the direction here, the surface layers continually get less, continually are deflected. Northern Hemisphere picture again. And this produces a net deflection, which is perpendicular typically to the wind direction, producing the effect of the spiral and the net movement of the water that's quite different to the wind. So we get this net transport effect. This becomes really important when we have major storms. If we have something like a major hurricane that we're seeing here off the coast of Florida, this is going to produce a circulation, in this case in this direction as shown here. The movement of these winds and currents that's adjacent to the coast is going to produce a net pumping action, or a net movement of the water towards the coast. And this produces a characteristic associated with storm surge, associated with this particular hurricane structure in this case. That storm surge will produce some dramatic effects sometimes. So as a direct result of that Ekman transport, powered by those strong winds, we get an extra amount of flow into the coast, which can add to whatever is taking place as a result of the normal tidal action, and perhaps as the result of normal wind action as well. And we can get very severe surface flooding and severe damage associated with that. And the storm surge can be sometimes as many as 4 or even 5 meters in rare cases, which can cause tremendous extra suffering and problems. The chapter does a very good job at looking at these, the sort of the basic structures that we end up in the ocean with, gyres, with flows around. These are associated with pressure gradient forces and wind effects. We get Ekman transport, and those things together produce a variety of interesting secondary effects that include the Walker cell, which we'll review, basin-wide tilt, and the resolution of this two-layer ocean in this up and down welling. Formation of the gyre is when we got water flowing around the surface in a circle in this particular way. That net pumping action, as a result of this, there's a gradient due to the formation of this hill, this mound that's formed in it, and that's going to produce an outward flow. But the movement of the water through the Coriolis effect tends to drive the water in the inward section, and we end up with an equilibrium, a geostrophic equilibrium as it's called, that's associated with the balance of the gravity force, which tends to make this hill smaller, and the Ekman effect, which tends to make the hill higher than it would be, or the hill to rise. What's very interesting as well is that we get the possibility of something different as a result of this Ekman approach, and as a result particularly of this deflection. Over the equatorial area, we have the formation of the Hadley cell. The Hadley cell in a non-rotating Earth would tend to produce a flow of air that's from the north to the south in the northern hemisphere, and from the south to the north in the southern hemisphere. But as a direct result of the deflection to the left in the south and a deflection to the right in the northern hemisphere, we end up with a net equatorial current, and we tend to get an accumulation of warm, high temperature water at the extreme western edge of the Pacific. If we've got relatively warm temperatures here and relatively low temperatures here, we tend to produce another convective cell. A convective cell, in this case, that spans the entire Pacific, and we end up with what's called the Walker cell, and the Walker cell circulation process, with high intensity rainfalls on the western edge, and on the eastern edge tends to be a much thinner thermocline and a significant drying effect. The dry air is return. That's where we get descending air. And so we get the accumulation of warm, relatively low density air. This suppresses the thermocline and allows it to come close to penetrating at the extreme eastern edge, which produces the possibility of having significant nutrients and significant photon arrangement or availability of sunlight as a result of the equatorial location. This produces some of the best fisheries that the Earth knows. And that's a direct result of Coriolis plus trade winds plus this effect of the Walker cell, of this net effect. So we tend to get a slight increase. We get this upwelling effect, all this taking place. We get a net circulation as shown from the high pressure at one side to the low pressure at the other side. This is caused by wind setup, the effect of that ocean-wide shear or force of the wind on the surface. And we get a Walker circulation that tends to produce this convective cell, as the book discusses very nicely. One of the wonderful things that happens as a result of this is we get the possibility, as the intertropical convergent cell migrates north and south of the equator as it follows the seasons, that the movement of this along the equator tends to produce an Ekman type effect, which pumps water up from the depths as well. And so we get a bit of a breakdown of that two-layer ocean as a result of the Ekman process that's occurring directly as a result of the Ekman process at the equator as well. And we can tend to get that movement, and the cold water comes up, bringing with it its load of nutrients and producing the possibility of significant additional productivity of the ocean at this level. There's a couple other ways that this breaks down as well. If we've got currents along the coast, then we get Ekman transport producing upwelling as a result of that surface effect, drawing in water to replenish the supply along a coast as we've shown here, or sometimes a pumping into the coast and producing downwelling as a result of the surface processes similar to our storm surge case. This produces an overall ocean pattern, which of course is immensely complicated as a result of the effect of currents and land masses, and seasons and differential heating, and all of the complexities of fluid motion. The one thing we can do here, harder to do perhaps if we do it in the book, is we can sort of bring in extra pictures here, and what we can imagine here is that overall Pacific gyre produces that peak of the hill, or that mound that occurs in the Pacific as a direct result of that gyre that's formed because of the Earth's motion. This produces the normal conditions, but is associated with many things that happen in life. You get an accumulation that establishes this and accentuates it. The movement of the air itself, in fact, tends to enhance this development of this flow along the equator, but it overshoots, and as a result, if this mound starts to slump for almost any reason, this cell becomes weaker and the mound starts to migrate more towards the center of the ocean. And this is characteristic of what the book talks about as these El Nino conditions as well. And so we get a breakdown of normal conditions, producing now a complete different pattern of circulation associated with high temperature mound of water in the center of the Pacific, with much reduced rainfall on the extreme western edge, and a very different pattern of circulation overall, with the thermocline being suppressed and therefore a very reduced amount of available nutrients taking place on the west coast of South America. The net effect of these things, of course, is quite dramatic, that we end up with very considerable human effects that are associated with these, where we get droughts, and we get fish dying, and we get flooding, and we get all sorts of complicated circulation taking place as a result of the interactions that take place across the ocean. We get this overall circulation pattern that's part of this as well. Again, the process is initiated really with the formation of this brine, which draws in high temperature air that produces the effect of this downflow, this subsurface flow, where we get deep migration. But in order to complete the whole circuit and make the whole system work, we end up with this complicated system of currents and ocean movement, with heat being released and being absorbed in different parts of the cycle. Fascinating and quite significant. What we end up having is a very significant amount of movement overall, where the total movement of energy from the tropical regions to the poles can amount at its peak to maybe as much as 5 times 10 to the 15th watts, which is 5 petawatts, or 5,000 gigawatts, or 5 million megawatts. And those are enormous energy transport mechanisms and of great significance for the Earth as a whole. So that's a quick overview. Go back to the book now, and I hope you'll continue and enjoy reading the final sections in Chapter 9. We'll see you at week 6.